Okay, tensorial spaces. Say first rank tensors often called vectors belonging to the vector space V. Vectors belonging to the vector space V. We do have, say, a vector space V equals set of, say, U, set of vectors, so-called vectors. Now construct a mathematical space V cross V. Construct the mathematical space V cross V equals UV, UW, VU, say AB. So we construct the mathematical space V cross V equals, let this be like this. Construct the mathematical space. This is called a second rank tensorial space. Second rank tensorial space we just call it as LVS, second rank tensorial space. This thing V equals, just to multiply two vectors as such. Here AB is not equal to BA. Restriction is that AB need not be equal to BA. Construct such a space. The members of this space are treated as ordinary mathematical algebraic objects. And we just think of this, we just have say, think of this mathematical object, say T, two arrows to denote that it is a tensor of second rank. I just write as sigma alpha beta summed over alpha beta lambda alpha beta u alpha u beta summed over all possible values of alpha beta. So these are u alpha u beta could stand for any of these objects belonging to the second rank tensorial space. Lambdas are scalars. This is called a second rank tensor. Here alpha betas are suffixes used to specify the identity of vectors. U alpha u beta need not be equal to u beta u alpha. In similar manner, we can construct a third rank tensor. This is constitute a second rank tensor, and the say set of all such quantities called second rank tensorial space. Set of all such quantities can be called a second rank tensorial space over the field of real numbers. Say T, S, P, the collection of all such quantities constitute a second rank tensorial space. Similarly, we can construct a third rank tensorial space, etc., or nth rank tensorial space, and so on and so forth. And these are called tensor product of vectors. These objects are called tensor product of vectors. Now consider Hereafter, okay, hereafter, to make the to have greater simplicity, we are not at all making use of this type of sign. Say often, if you are very particular, you can add these two objects, second rank tensors, and put two arrow to show that it is the tensorial addition of two tensors, if you are very particular. But to make the thing very clear and simple, we just hereafter we shall simply use this ordinary sign of addition. And instead of putting, say, alpha star A, we simply write alpha A for sake of simplicity. This is for sake of simplicity. Otherwise, there shall be a clustering of symbols. So we may not say we may not have any possibility of say economy of thinking. Clustering with the symbols does not lead us to any new thought. So simply we can just write on the basis alpha star A is simply alpha A, etc., etc. Or alpha, say, T. Here it is multiplied with a second rank tensor, but we can just simply write as alpha T, alpha second rank tensor T. Instead of putting any other arbitrary symbol here, just to put alpha times tensor T, that would do. Like here, like we have put here. So here we do have tensorial, we have constructed a tensorial space of second rank tensorial spaces, and all algebraic properties obeyed by vectors to construct, say, vectorial space can also be used to construct to build up all the mathematical properties of this tensorial space. And we can have, say, lambda AB, I simply write as lambda A into B, and this is also equal to A times lambda B. These mathematical objects are identical. Lambda A into beta B equals alpha beta AB. Here alpha beta belongs to R. Alpha beta belongs to R, real field. Then I can write A into B plus C equals, simply I write as AB plus AC. AB plus AC, and AB plus AC, AB plus AC when multiplied with C gives AC plus BC, so on and so forth. Say lambda AB plus CD equals lambda AB plus lambda CD. Then let T is equal to, second rank tensor T equals AB. Then lambda second rank tensor T equals lambda times A B plus B equals A times lambda B. Now zero second rank tensor, I put it like this: second rank zero tensor 0, 0. Vector 0, vector 0, vector 0 times 0 tensor. Second rank tensor. And T, second rank tensor T equals 0 second rank tensor equals 0 second rank tensor plus T, and this 0 second rank tensor is additive identity existing in second rank tensorial space. This is additive identity existing in second rank tensorial space. This is tensor T. And 0 times 0, vector 0 times vector A gives second rank 0 tensor. And S plus T tensor equals T plus S tensor, belonging to that linear vector space over the field of real numbers. LVS of second rank tensorial space belongs to second rank tensorial space. And for any second rank tensor, there exists its own additive inverse. Say vector the second rank tensor A plus minus second rank tensor equals 0 rank second rank tensor. This is additive inverse of this second rank tensor. This is true for any A second rank tensor belonging to LVS, say second rank tensorial space. Second rank tensorial space. So, the tensorial space over the field of real numbers obeys all the algebra obeyed by vector space. So, tensor can be defined as a vector belonging to the product vector space. That is how a tensor can be defined. A tensor is a vector belonging to the product vector space. That is called a tensor in general. Then we come to linear dependence on a first rank tensorial space over the field of real numbers. Linear dependence of vectors. Linear dependence of vectors or linear dependence of first rank tensors over the field of real numbers. Linear dependence. Say dependence of first rank tensors A first rank tensorial space, say vectorial space V, set of all VI's, all vectors I belonging to say I belonging to I, which is could be identical to 1, 2. Say consider index, set of indices I could be say 1, 2, 3, etc. A vector space, first rank vector space. That is a vector space, first rank tensor space. Now construct the object, mathematical object, say of non-zero vectors. Construct non-zero vectors, say say lambda 1, say v1 plus lambda 2 v2 etc. lambda say n or lambda m lambda n say vn. Construct this mathematical object and call it as a vector A. Here these are all non-zero objects, that is vi is not equal to 0 vector, or v1, it means simply this, v1 non-zero vectors, v1 v2 v3 vn etc. are non-zero vectors, and the lambda i's are real scalars. Lambda I is say real scalar, that is lambda I belongs to the real field, and 1 2 3 etc. only suffixes to pin down the individuality of real scalar. It does not denote power of scalar, it is just individual. Lambda 1, lambda 2, lambda n are scalars, simple scalars belong to the real field, and these things over lambda does not show any power of that lambda, just simply to specify the particular lambda. And this is the vector we have constructed out of n vectors. Say n vectors are there, we just constructed a mathematical object, say vector A. Then these vectors are said to be linearly dependent. This set of vectors v1 etc. vn are said to be linearly dependent if not all lambda i's are 0. If not all lambda i's are 0, then these non-zero vectors, these are all set of non-zero vectors, non-zero vectors. These vectors v1 v2 vn etc. are non-zero vectors, and if this is equal, if this is not, all of this is not equal to 0, then excuse me, zero vector here. This is the mathematical object I have constructed. I just added all these vectors linearly just by multiplying all these vectors with the scalars, and I just simply added and I got 0 vector. And if not all alpha i's are 0, then this v1, this set of vectors is said to be linearly dependent. This is vectors A, what I have put here should be 0. I constructed a 0 vector out of n vectors by adding all these n non-zero vectors, by constructing lambda 1 v1 etc. and just add it, and I got 0 vector. And if not all alpha i's are 0, the beta i's, say lambda i's are 0, that is 0, then we say that this set of vectors constitute a linearly dependent set of vectors, linearly dependent, because any vector here can be expressed as the sum of other vectors, linearly depending upon the other vectors, linearly dependent. Now linearly independent set of vectors. Now we come to concept of linearly independent set of vectors. Now same way, the set of vectors, n vectors are said to be, non-zero vectors are said to be linearly independent if this condition is satisfied, such that all alpha i's are 0, all alpha i's are 0, then lambda i's are 0, then this set of vectors are called linearly independent set of vectors. It is a basic fundamental concept in vector analysis. It gives say dimensionality of vector space. Dimensionality of vector space. So we do have, first we have constructed say a set of we just constructed this mathematical object out of n non-zero vectors. Out of n, each vector is not zero, and after multiplying with scalars, lambda 1, lambda 2, lambda n scalars, we just added everything, but we got a zero vector here. Then we say that if all lambda i's are zero, if all lambda i's are zero, then we say that this set constitutes a linearly independent set of vectors. Linearly independent set of vectors. So we now come to the concept of dimensionality of vector space. Dimensionality of vector space. If there exists, say, n linearly independent vectors in a vector space such that every n plus 1 non-zero vectors are not linearly independent. We consider a vector space in a vector space having, say, construct a vector space. Now add all these non-zero vectors such that this is equal to 0. We do have all lambda i's are 0. Then this set of vectors v1, v2, vn constitute a linearly independent set of vectors. These are all non-zero vectors. So in a vector space there exists n linearly independent set of vectors such that every set of n plus 1 non-zero set of vectors are linearly dependent. Every set of n plus 1 non-zero vectors are linearly dependent. Then we say that it is a vector space of n dimension. That is a vector space of n dimension. Given concept of dimensionality of vector space. Okay. Then the cardinality of vectors, a very basic fundamental concept. A very basic fundamental concept in vector space. The cardinality of vectors in the vector space is uncountably infinite. Cardinality means number of vectors in any vector in a vector space over the field of real numbers. Number of vectors in a vector space over the field of real numbers is always uncountably infinite. So out of that uncountably infinite number of vectors in an n-dimensional vector space, there exist n linearly independent non-zero vectors. That is a basic fundamental concept. That is very basic fundamental concept. Okay. Now, in an n-dimensional vector space, any vector, any non-zero vector, in an n-dimensional vector space, any non-zero vector can be expressed as the sum of these linearly independent vectors, set of the linearly independent vectors. So vector, I write vector v. Vector v is equal to sigma, say I is equal to 1 to n-dimensional vector space. We speak about n-dimensional vector space. Dimensionality of vector space is n, or let me put as capital N, that is better I think. Here n is already have taken. So alpha I vi are all non-zero vectors. So this is a non-zero vector. Then in an n-dimensional vector space, any non-zero vector can be expressed as the sum of all these vector non-zero vectors v1, v2, v3, vn, etc. And we assume that it can constitute a basis in an n-dimensional vector space. Basis in an n-dimensional vector space. Yes, basis next. Basis in an n-dimensional vector space. Basis. So we have an vector space of n dimension. The cardinality of vectors in a vector space over the field of real numbers is always uncountably infinite. And if the vector space is of having n dimension, then any vector, a non-zero vector, can be expressed as the sum of these vectors, non-zero vectors, n non-zero vectors. Okay. Now we think of the existence of what is called basis in an n-dimensional vector space. Consider this set of non-zero vectors ei, set of non-zero vectors such that I equals say 1, 2, 3 up to n. A set of non-zero vectors ei equals 1 to n. It is called a basis in an n-dimensional vector space. And we can have any type of basis. Say you can think of another type of basis, say ei dash equals I being going to, I is equal to going from say 1 to n. This is primed basis. This is, we call it as primed basis. This is unprimed basis. So any number of bases you can construct in a vector space. So the property of basis is always, now I have already told you that any non-zero vector can be written as the linear combination of the basis vectors in an n-dimensional space. Linear combination of basis vectors in an n-dimensional space. Okay, so vector A I write as ai, scalar ai, vector ai summed over I equals 1 to n. Summed over I is equal to 1 to n. This is a non-zero vector. This is written as, say, they are written as the sum of the basis vector a1. Say I have just write as a1 e1 plus a2 e2 plus etc. a n en. Now, so these are scalars. a1, a2, a3, an represents the particular vector with respect to the basis ei. With respect to this basis, these ai's can represent the vector a. Now, this representation is always unique. That we can easily show. This representation is always unique. How? This representation is always unique. Say, I write vector, the same vector A equals sigma, say, a I star ei with respect to the same basis. I is equal to 1 to n. I want to show that ai star is equal to ai for every I. How? Simple thing. This is equal to, this is also equal to sigma over I 1 to n ai ei. Then vector A equals sigma over I 1 to n, say ai star minus ai times ei equals, this is a minus a minus vector a minus vector a. Okay. This is vector A, So add, subtract one vector from the same vector. So this is equal to 0 vector. Left hand side is 0 vector. So this is 0 vector. So we have considered 0 vector. So what does it mean? Equals I is equal to 1 to n. Say this I called as say alpha I ei equals this 0 vector, showing that all alpha i's must vanish because this set constitute a linearly independent set of vectors. Ei, set of ei constitute a linearly independent set of vectors. So all alpha i's must vanish for every I. All alpha i's equals 0. All alpha i's equals 0 means that ai star equals ai. So representation of a vector with respect to a particular basis is always unique. Always unique. That uniqueness is already proved. And in anticipation to the future development of theory of tensors, I name these AIs as contravariant components of the vector A. I christen it and call AIs. I put the name. Christen means I put the name, impose the name. These AIs are called contravariant components of the vector A. AIs are called contravariant components of vector A. In anticipation to the future development of tensors, I call this is as contravariant component. Contravariant components of vector A. Contravariant components of vector A. Now we come to the famous convention proposed by Einstein, the greatest scientist ever lived in human history. They are very funny, very great man. No one in the world history can be compared with our great Einstein. He proposed a convention because writing all this sum, etc., summation convention is very, very strange, and we can't carry out all the mathematical, say, manipulations just having this sign here, sigma sign. To remove the sigma sign, he simply suggested an, say, summation convention. Summation convention. So he just, instead of writing, say, sigma over I 1 to n ai ei, simply wrote is identical to ai ei, and he told you this summation convention, you can keep it in your mind. Assume that it is already summed. How? One superscript is there, I is a superscript here, and this I is a subscript, so it is a dummy suffix. Assume that whenever a superscript followed by another subscript here appears, you just sum it in your own mind. So he told it both save space and time. How? Putting this thing is, space is lost. Just by putting the sigma sign, space is lost. And so if you ignore it, you can save space. And if you ignore it, you need not write it for wasting time. So he saved both the space and time just by ignoring this summation. This is called Einstein convention. He himself told it is a great discovery. Because we have saved a lot of space here, saving space and time. So Einstein could save both the space and time by ignoring this sigma sign. He just simply wrote A is equal to AI EI. Simply that will do. Ignore it. So he is a space-time theory of relativity man. So that time he thought of ignoring it. So he could save space and time by ignoring the sign convention. Whenever a suffix occurs both in superscript and subscript like this, you can just simply ignore it and write AIEI. Very simple thing. That is famous Einstein convention. So now we come to the concept of transformation of basis. Transformation of basis. Vectorial basis in an n-dimensional vector space, EI basis EI, I equals 1 to n, and another primed basis EI dash, I equals 1 to 2 basis, vectorial basis. Now I just construct a relationship between this EI and EI dash. EI and EI dash, I write EI dash, vector EI dash, I just simply write as vector EI dash is equal to lambda I dash j, Ej summed over j. Using Einstein convention, I simply write as lambda j I dash Ej using Einstein's summation convention. Lambda linear, here the vector EI dash is written as the linear combination of the basis vectors according to the vector analysis, according to the concept of linear independence, concept of dimensionality, concept of linear independence of set of Ej vectors. Every vector, I told you that every vector in a vector space, non-zero vector, can be expressed as the linear combination of the basis vectors. Here basis vectors are here Ej, set of Ej, and I write Ei dash, the primed vector Ei dash equals one of the vector, I dash vector in the primed basis, new basis, is written as the linear combination of the basis vectors belonging to the say unprimed basis. I just write like that, summed over j, and I can just put remove the summation convention on the say acceptance of Einstein summation convention. So I wrote like that. And Ij goes from 1 to n. Ij goes from 1 to n. Here you need not put I dash here. I dash means another I, simply I. So Ij goes from 1 to n. 1 to n. Then I write in the matrix form, matrix notation. The same thing I write in matrix notation and write matrix E1 dash, E2 dash, etc. En dash equals matrix lambda 1 1 dash, lambda 2 1 dash, etc. 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 lambda n 1 dash, lambda 1 2 dash, lambda 2 2 dash, etc. etc. lambda n 2 dash, then lambda 1 n dash, lambda 2 n dash, etc. etc. lambda n n dash multiplied with matrix E1, E2, etc. En. Matrix notation. So that is the meaning of that EI dash is equal to that matrix notation. This is in matrix notation. Of this expression. Matrix notation of this expression. This expression. I dash. Matrix form. Expressed like this. And in this matrix notation, we may regard lambda j I dash, regard lambda j I dash as the element of jth row. Jth row and ith column. Ith column. This lambda j I dash can be regarded as element of ith row, jth row and ith column of a matrix lambda, matrix lambda. This lambda j I dash can be regarded as the element of ith row and jth row and ith column of lambda matrix. Jth row and ith column of lambda matrix. So that this equation can be written in matrix form. This equation can be written in matrix form. This equation can be written in matrix form. Say vector E star equals lambda transpose E star, where this stands for, this E dash star stands for matrix, column matrix, E1 dash, E2 dash, etc., En dash, column matrix. And lambda stands for that matrix we have written, and this E star stands for the matrix E1, etc., En. This wavy form shows that is transpose of the lambda matrix. Transpose of the lambda matrix. Transpose of the lambda matrix. This is in matrix notation. In matrix notation. Transpose of the lambda matrix. Now, consider the transformation of components. Contravariant components of the vector A. Consider the transformation of contravariant components of vector A. We christen it as contravariant in anticipation to the future development of tensor theory. In future we call it as contravariant components. So, contravariant components, transformation of contravariant components of vector A. We have vector A with respect to the primed basis A I dash, E I dash is identical to A K, E K, summed over K. This is with respect to the old basis. This is with respect to the new basis. So two different bases are there. Only a single vector is there. We represent the single vector is equal to ai dash, ei dash with respect to the primed basis, new basis is also identical to ak, ek with respect to the old basis. Now we have ei dash is equal to ai dash equals ei dash. And what is ei dash? Lambda I dash j. Lambda I dash, let me call it as k. Lambda I dash k ek. This thing, which one? This ei dash, I write as, see, ei dash equals, instead of j, you can put k here. So you have substituted this here. So ai dash lambda k I dash ek minus ak ek equals 0 vector. This thing I have taken the left hand side and wrote as 0 vector. So this is 0 vector. Then I take ek outside on the right hand side and write ai dash lambda k I dash minus what else? Ak times ek equals 0 vector. What does it mean? It means that this term within the bracket times ek summed over k vanishes, showing that the term within the bracket must vanish, because this constitutes linearly independent set of vectors ek, set ek, e1, e2, ek, en constitute a linearly independent set of vectors. Then the term within the bracket has to vanish, and we write say ak equals ai dash lambda k I dash here. That is the transformation formula for components of the vector, contravariant components of the vector. Contravariant components of the vector. Now, interchange the role of the primed and unprimed basis. So, without loss of generality, we can interchange the role of primed and unprimed basis. So, wherever a dash is there, just remove this dash, and wherever dash is not there, you can put dash there, because you can just simply change the role of primed and unprimed basis and write, and you can write ak dash equals say ai lambda k dash I just interchange the role of k, this primed and unprimed basis, interchange it. So this is the expression you have got, transformation formula for this ak dash, a component with respect to the primed basis. So this I just simply write as lambda k dash I ai ak dash. That is the transformation formula for the say contravariant say components of the vector A. Now this I write in matrix form. And write let it be like that. Yeah. Okay. Now consider transformation formula for our, say, this is ei dash expressed in terms of the old basis. Now ek or ek, I write ek is equal to lambda, say k here, I dash here, a. Interchange the role of primed and unprimed basis. I can write like this. So here I can substitute this ek here in this expression. So ei dash substitute in that expression. So ei dash, I write ei dash is equal to lambda I dash here, lambda I dash here, then k ek, that is equal to lambda k I dash. Ek, instead of ek I can write lambda k here, then j ej, I write like. I express ek in terms of ej dash, j dash. Okay, fine. It is fine now. So ei dash is equal to lambda k I dash into lambda j dash k ej dash. This is right hand side is equal to simply delta j dash I dash, delta j dash I dash ej dash. This delta a j dash I dash is chronicle delta. Delta j dash I dash is chronicle delta. Delta j dash I dash is chronicle delta. So we have the expression lambda k I dash lambda j dash k equals delta j dash I dash. It's chronicle delta. Now take the matrix of this, matrix notation of this. Simply take the matrix notation of this expression. Take the matrix notation of this expression. So when you take the matrix notation, lambda matrix lambda k I dash into matrix lambda lambda j dash k equals matrix delta j dash I dash, which is identity matrix I. Identity matrix I. Identity matrix I. Okay, fine. It is good. And this is nothing but matrix lambda. Matrix lambda. Matrix lambda into matrix lambda k dash j equals identity matrix. So lambda k dash j is the inverse matrix of lambda. Matrix lambda k dash j is inverse matrix lambda inverse. Lambda inverse. And we have the transformation formula for our contravariant components of the vector. What is that? ak dash equals lambda k dash I ai. Lambda k dash I ai. Now take the matrix form. If you take the matrix form, you write matrix ak dash is equal to matrix lambda k dash I times matrix A. Matrix notation. In matrix notation, we can write like that. What is this? Lambda k dash, matrix lambda k dash I is nothing but lambda inverse. Lambda inverse. So I write, say, matrix. This I write as matrix A star dash is equal to lambda inverse matrix A star. This I called as matrix A star. AI. Okay, fine. So compare these two equations. This is transformation formula for basis in matrix notation. Transformation for components of the vector. So compare these two. Then, say for sake of simplicity, let me put Q is equal to, matrix Q is equal to, let me put, say, E star dash. It is equal to matrix Q times E star, where Q is equal to lambda transpose. Lambda transpose. Then what shall be the matrix inverse? This fellow, lambda inverse. Now take the inverse on both sides. Say Q transpose. Then Q transpose is equal to lambda. Then inverse of Q, inverse, take inverse of lambda. So Q transpose inverse equals lambda inverse. Q transpose inverse is equal to lambda inverse. So I write this equation I can write as E dash star is equal to Q. Lambda inverse is equal to Q. Lambda transpose is equal to Q times E star, and this fellow A star dash is equal to what else? Q transpose inverse of what else? A star. Compare these two relations. Thus the law of transformation of contravariant components of a vector A is given by inverse transpose matrix of the law of transformation describing the basis change of basis. This is basis change, transformation for basis change, q times this. This is transformation for components equals inverse of transpose of the basis change for this thing. That is why we call these A components contravariant components of the vector A. That is how the name comes, because of this. This is Q times this basis. This is components, matrix of components, contravariant components transforms like this, Q transpose of inverse. That is why these AIs are called contravariant components of the vector A. Contravariant components of the vector A. Contravariant components of the vector A. Additional structure, I introduce an additional structure in the vector space. Cos V to real field R. To is equal to, say, lambda belonging to R. In ordinary notation I write, say, u dot V is equal to scalar lambda belonging to the real field R. So our LVS become, linear vector space become an inner product space, or V becomes okay. Our LVS becomes an inner product space, an inner product space. LVS becomes an inner product space. Properties of inner product. Properties of inner product. Yeah. Say u dot V is equal to V dot U. Then u dot V plus W is equal to u dot V plus u dot W. Then lambda times U dot V equals lambda u dot V. Lambda belongs to R. We consider only that LVS over real field such that u dot V, u dot U is always mod U square, which is always greater than or equal to 0, and it is equal to 0. It is 0 if U equals 0. 0 vector. We consider only the space for which u dot V is expressed in the form, only the space for which u dash V is written as mod of U into mod of V into cos of the angle between UV into cos of the angle between UV. That is, say, that is equal to mod of U into mod of V cos theta. theta is always real. Theta is always real. Now, next. Reciprocal basis or dual basis. Reciprocal basis or dual basis. Reciprocal basis or dual basis. Suppose we have an LVS over real field, then we let that vector space be spanned by the basis EI. I belongs to 1 to n, spanned by the basis EI. Now, we introduce what is called the dual basis, being dual to EI. We introduce dual basis, being dual to EI. I belong to 1 to n, such that EI dot EJ is always equal to delta Ji. Delta Ji. So this is called the dual basis, being dual to this basis. Dual basis. EI dot EJ equals delta Ji. Equals 1 if I is equal to J, not equals 0 if I is not equal to J. This is dual basis. Dual basis or reciprocal basis. So we write, say, if you take their dot product and write, say, EI dot EJ equals delta Ji, which is equal to mod EI into mod EJ into cos of the angle between EI, EJ, that is delta Ji. Delta Ji. This I write as a EI mod EJ into cos, I write as theta Ji, delta Ji. Cos theta Ji. Theta Ji is the angle between EI and EJ. Now, it necessitates to define the dot product, say EI dot EJ. EI dot EJ equals, I put it as Gij, and EI dot EJ equals G superscript Ij. And these Gij, these Gijs are called very important mathematical object in physics. Very most important mathematical object in physics is called covariant components of metric tensor. covariant components of metric tensor. Metric tensor of space. It determines the geometrical property of space. The nature of space, geometrical, whether the space is curved or space is flat, everything is determined by this important tensor, covariant components. This is called contravariant components of the metric tensor G. Contravariant. Oh, where? Oh, where it won't. Contravariant components of metric tensor G, second rank metric tensor G. This is covariant components of second rank tensor metric tensor G. Covariant components. Covariant and contravariant components of the, and they determine the geometry of space. This Gij determines the geometry of space. Geometry of space. In general theory of relativity, this Gij represents gravitational potential in Einstein's theory of gravitation. In Einstein's theory, this Gij represents gravitational potential in Einstein's theory of relativity. Gravitational potential in Einstein's theory of relativity. Gravitational potential in Einstein's theory of relativity. So very important tensors, Gij and its contravariant components. And we may write, say, a tensor, second rank tensor G. In anticipation of the future development, I just write second rank tensor G equals Gij. I simply write as Ei Ej. This is second rank tensor. And is also equal to Gij Ei Ej. Second rank tensor G, second rank tensor G. This is the geometry of space, is purely determined by this tensor. The whole of Einstein's theory runs is to determine this mathematical object in general theory of relativity. And Einstein himself took, say, 8 years to solve his field equation to determine this G. 8 years he took to get to value of this, taking sun at rest and planets moving around the sun, and he solved his equation, most famous field equation called Einstein's field equation. This is Einstein's field equation, G equals minus KT tensor, Einstein tensor, and this is energy momentum tensor. This G, capital G, contains this fellow. So it took 8 years to find out this, say, out of that. That is the greatness of Einstein. Only Einstein did it. So this is how things happen. Now we have any vector A is equal to, with respect to the basis, say Ei, I wrote like this. Now with respect to the dual basis, I write like the AK, EK, with respect to the dual basis. The same vector A with respect to the dual basis. This is with respect to the basis Ei. This is with respect to the basis Ek. The same vector. AK. This AK. K is the subscript here. I is the superscript here. This we called it contravariant components. Components of vector A. This we called it covariant components. We shall call it components of A, vector A. Only a single vector viewed from two different, say, basis EI, this and its dual basis. Contravariant components and covariant components. Okay. Now let us find out transformation law for AK. So I write vector A equals, say, A K dash, EK dash equals AI. This is EI superscript. Now I want to establish transformation law for connecting this EK dash and EI. Transformation law connecting EK dash and EI. Okay. We have, say, this transformation law, say EI dash equals lambda I dash EM. This already we know. Now we shall establish. Now you dot on both sides. You dot on both sides with dot this equation. Dot this equation on both sides. With EM dash. Dot on both sides this equation with the EM dash. Then we shall have say AK dash, EK dash dot EM dash equals what? AI EI dot EM dash. This is our chronicle delta in the primed basis. Chronicle delta in the primed basis, and we write, say, AK dash equal delta K dash M dash equals AI EI dot EM dash. So left hand side becomes simply, say, AK AM dash. Left hand side equals this, equals AI. This fellow, how to find out this fellow? That is a EI dot EM dash. EI dot EM dash. Now we have EM dash equals lambda M dash here, say J, Ej. Now dot on both sides with Ei. Dot on both sides with Ei. This expression. Dot on both sides with Ei. Then we shall have, say, Ei excuse me, dot on both sides with, say, superscript Ei, not that Ei, superscript Ei. So, Ei dot Em dash equals lambda Jm dash Ej dot Ei dash dot Ei. On both sides you dot with Ei. So on right hand side what you get is simply lambda j m dash delta ij. So what do you have on right hand side? Lambda I m dash. So Ei superscript I dot em dash is equal to simply lambda I m dash. So I have the transformation law here. This is lambda I m dash Ai. E m dash. Sorry, A m dash. A m dash. So this is identical to here. For basis transformation we wrote E m dash is equal to lambda m dash. So we write so Ei equals Gik Ek we wrote. Now dot on both sides with Ej, subscript Ej. Dot on both sides with the subscript Ej. Then we have Ei dot Ej is equal to Gik Ek dot Ej. So left hand side we have delta, very important relation, delta Ij equals Gik, very important relation in theory of relativity, Gkj, very important in relation theory of relativity. This equation, determinant of this equation, say Gij Gjk equals delta Ik. Taking the determinant of this equation, Gij into determinant Jjk equals determinant delta Ij, which is equal to 1. Okay. Equals 1. So determinant Gjk I put simply as small g. So determinant Gij becomes 1 over small g. small g. And say any vector I wrote say vector A, V is equal to Vi, Ei. Now dot on both sides with Ek. V dot Ek equals Vi, Ei dot Ek. So that is equal to Vi delta Ki, that is equal to Vk. So Vk is nothing but the dot product between vector V and Ek. That is a fundamental expression often we use in say even in quantum mechanics. In quantum mechanics, such a fundamental expression we shall be making use. Say, for example, you consider, say, three-dimensional Euclidean space. Say a vector A we write as I times a three-dimensional Euclidean space, simple space Ay plus K times Aj, Az. Then Ax I write like that, I times I dot A, Ay is equal to J dot A, then Az. In say Euclidean space, we introduce Cartesian coordinate system, so K dash, K dot A. So we may write vector A simply write like this, I, second rank tensor I, A plus JJ, like tensor JJ, vector A, plus tensor KK, vector A. So vector A, I write vector A is equal to say II, tensor II plus tensor JJ plus tensor KK, tensor KK dot A. This is often called, this is our say identity tensor, and also it could be identified as metric tensor of space. Yeah. Identity tensor, metric tensor of space. So any vector, when you put dotted with the metric tensor of space, you yield the same tensor, same vector. So you shall get back the same vector. So now suppose you take a second rank tensor, dot it with G. Let us see what happens. You shall have second rank tensor, I write like that. Say I put say Tij Eij dot. For second rank tensor I write say G Lm Em. Now dot it. So I write Tij Glm Eij dot Em. So this is equal to Tij Glm Ei. This is delta Lj Em. So replace L with J. So you have replace L with J. You have this here. EM here it comes, sorry. EM. EM here. Now you combine these two fellows. Then this M is lowered to J and you write Tij. This is index lowering operator. Ei, Ej. This is M is lowered to G, Ej. So you got back the same tensor. Same tensor you got back. So whenever you dot product, construct the dot product with a tensor with a second rank tensor, say with our metric tensor, you get back the same tensor. That is a property of metric tensor of space. Now more about the component, more about the transformation coefficients. Consider the transformation. Madhya, okay. Okay, for the, okay. A set of talk I am going to have here, and it is to honor two great scientists in India, Dr. C. Sivaram of Indian Institute of Astrophysics and Dr. A.V. Gopala Rao. He published more than, Dr. C. Sivaram published more than 200 papers in most prestigious international journals. And similarly, Dr. A.V. Gopal Rao, he has also published the papers. And his work is spectacular. In group theory also he has put forward his effort to and establish his own, say, his ability to, and he produced a lot of PhD students, on, say, group theory. Also in quantum optics he did a lot of work, and yeah, I do have great regards for my friends Dr. C. Sivaram and Dr. A.V. Gopala Rao. I often ask a lot of doubt to both of them. They instantly clear all the doubt whatever I do ask to them. So I am very grateful to my friends Dr. C. Sivaram and Dr. A.V. Gopala Rao. Thank you.